down know that I'm not prepared, and I don't trust myself.
The kids got their mouth
that's
open
pretty
pretty big
I'm
there.
in the same boat, actually. I was doing like
Is that your kid? Is that your child?
today, and I was
Yeah, that's my
for,
kid.
like, the
Is it?
Practicing
and I was
now,
like,
you're like, I was like, oh shit. And I'm like looking for
That's
guinea
good.
pigs in this assist.
Do you have kids?
I gotta go review all of them.
That's good. That's good.
No, I have no
That's good.
I do not know how to study whatsoever. One bit.
Sorry to ask you all those personal questions. Sorry.
No, it's just not working.
Yeah, you just kind of move through it. You just, you're like, all right, well, I'll just live my life getting.
Wait, now we're talking about the bathroom again? I was trying to change the subject, for God's sake.
This is so funny. It's unbelievable.
Guys.
I think I experienced it. How about that quiz, Dr. T?
Midway.
Yeah, luckily Cormac sent me, yeah, you guys never saw it, did you?
No.
No. So Cormac sent me an email saying, hey, I can't see it.
Oh.
And then I was like, that's okay.
Cormac.
No, it was like less than an hour before class, so it wasn't like, you know.
Nice timing, Cormac.
Yeah, no, that's really good timing.
It is good timing. And then I was like, well, it should be there. And he's like, well, I can't see it. And I was like, I went and looked, and there's like, I had it in, there's too many buttons that need to be pushed to make the shit happen. I did not push one of the buttons. So it is now the quiz for Pi Day, Friday, 3/14. Okay? It is visible, theoretically. Someone let me know way too late, and then nothing can be done about it.
Are we doing anything more provided? That's a math
No.
class.
We're just doing math.
I mean, but okay, hear me out though. If someone would have emailed you at like 9:30, would you have opened it up?
Yeah, but I would have given everybody extra time anyway.
Alright.
Like actual time till Friday.
Does anyone actually do them like a day, more than a day ahead of time? Or does everyone wait till the day
Hour
of?
tops.
I go the day before.
Hour
I do the
tops.
night before.
You do them the night before? Night before? Cool.
I mean, they take like, they don't take that long.
I usually do it at like 11 a.m.
Why didn't I hear from you last night?
So I was like, I didn't tell someone if there was a big deal today. I was like,
All good.
I was like, I thought he mentioned something about
Nice.
the class.
Yeah, but it's not there,
It's not
so
there, so I guess-
must have been hallucinations.
Too busy thinking about the math class. So
All right, good God. Yeah, so the quiz is now for Friday. It's the chain rule. Easy enough. I gotta have midterm grades figured out tomorrow. Did I already talk about how that was gonna roll?
You're right.
apparently midterms are due today.
I thought they were due today.
That's how it is.
But that's what my other teacher said.
That is what Dr. R told us, is that they were due on Wednesday.
Well, I'm working by tomorrow. Really?
That's what Dr. R said. I don't know. I'm not a professor. I don't know. What do I know?
Well, I haven't received any angry letters, emails yet, but I guess I'll have that to look forward to when I get home.
Well, they were only due, 2 hours ago, if anything, so you got it.
Got
That's
some
usually
time for the
Thursday.
emails start rolling.
That's
in.
ridiculous. Why would they, anyway, whatever. I'll just have to make some shit up, I guess. So, oh, we don't want to start red. No, not red. Start blue. This is not one of my blues either. Not bad. Oh, all right. So, onward. Calculus. Today we're going to talk about directional derivatives and the gradient. And this pen is already
I know.
so.
I was just talking about this.
About how the, you were talking about the gradient?
Well, I was kind of.
That's cool.
Just
I like that.
Not really, but kind of.
Sadly.
Daniel, we
Wow.
use a gradient on our AMAC homework.
Okay.
Sadly.
Let's start off with the chillest. For us, this is the chillest scenario. 2 inputs, 1 output. Let's say I've got a level surface view. So we're gonna look at the level curves here of this thing. And let's say it looks kind of interesting. Do a little kidney shape there. A little kidney, something like that. And it gets more circular and then something like that. So these are the level curves. Do you remember what that means? It's a face down, we're looking at straight down, the z-axis is coming out of the board. And this would be, for example, z equals 10. And this is z equals a different level. And this would be z equals, I'm just making these up. But these are different height curves. So the height is constant along these curves. So z equals 3. So what shape is that actually? Like in 3D, what does that look like? Yeah? With a little dent in the side, kind of, yeah. So imagine a hill is ahead of you, and there's almost a little valley that kind of goes up to the peak, kind of like that. Does everybody see that? Okay. All right, cool. So we might be interested, and we will often be interested in being at some location. So this would be x naught, y naught. And trying to determine the slope in a given direction. So this is a slightly different problem than we've had before. So I'm here on this surface, and I'm trying to figure out what is the slope when I look in any particular direction. Now notice this way, let's just make some observations here. Would the slope be positive or negative looking, this is the direction I'm looking toward the tip of the pen?
Negative.
What'd you say?
Negative.
Why'd you say negative?
It has a little slant in there.
So am I going up or down? So think about the actual surface arc.
Oh.
Am I going up when I move it? If I walked this way,
Yeah.
am I going up or down?
You're going up.
Going up, so the derivative would be positive. Does that make sense? So just thinking positive slope. So it's a lot like normal derivatives and slopes, except that we have the possibility of different slopes in all the different directions. What would this derivative be, positive or negative in that direction? Negative, because you're moving down. And we're gonna find out that if I moved this way, what if I was moving along this actual level curve? What do you think the derivative would be?
It would be 0.
It would be 0. Because if I'm not changing height, if I'm moving on one of these level curves, I'm not changing height, and so I would expect the derivative to be 0. So think about that, derivative 0 in this direction, positive in that direction, negative there, and then maybe in this direction also, the tangential direction, that would also be 0. But we'll make that all very solid. I'm just trying to give you a little intuition about what you're about to see. So there is x naught, y naught. We're gonna pick a direction. So we're using a direction vector u, and it's a unit vector because we don't want it to convey anything other than direction. We don't want magnitude conveyed by the u vector. So I'm gonna have a direction vector u, and I'm gonna take that in kind of a way, the same way that we did the derivative in the x direction, derivative in the y direction. First off, let's talk about this. This is a unit vector. And we're gonna think about a curve that is just, we're gonna think about a line that is in the direction of u that passes through the point x naught, y naught. So envision the line in the plane, in the xy plane, through x naught, y naught, in the direction u. And u, let's give u some definite components, so we'll call them u1 and u2. So what would that curve look like? We would say it's something like r of t, well, how about we call it L of t, because it's a line. L of t equals the point that we want to pass through, plus t times our vector. And I hope that that makes sense now. We kind of did that last time, that would be the equation of this line right here. Well, you know, imagine it actually was drawn properly. Like there. So essentially what I'm going to do is I'm going to take my function f of x, I'm going to restrict it to this line, And that turns this into a function of one variable. So think about that. So now, restrict f of xy to this line. That line depends on t. And so you're taking this thing that was two variables and turning it into a one variable thing. So in other words, I've got f of x naught plus tu1, comma, y naught plus tu2. And I'm just plugging in these. If you're not quite seeing where I'm getting that, you could write this in vector form like this. Just combine the vectors. That's the x, and that's the y coordinate for any t. And so we're plugging those into the function. And now I'm going to take the derivative of this with respect to t. And so it's a chain rule, actually, right? Because I've got f that depends on x and y, and each of those depends on t. And I want to take the derivative with respect to t. So this is going to be kind of a different thing, and I'm going to use a slightly different notation for this. I'm going to say d in the direction u, so capital D, that's a directional derivative, in the direction u of f at x naught, y naught, is equal to the derivative with respect to t of this new function that we have. So we're going to put here d dt of this f of x of t, y of t, which is this thing, this thing. So now chain rule says, the way that works is I take the partial of f with respect to x, and I'm going to evaluate that at the point I'm interested in. So that's partial with respect to x, and then dx dt. So let's just put x dot of t right there for derivative with respect to t, or put a prime if that makes you feel better. That's the derivative of this with respect to t. And in a minute, I'm going to use this formula to make it simpler. Then plus, so make a little note here also, this is the chain rule, the multivariate chain rule. The derivative of f with respect to y, and that's a partial, at x naught, y naught, then times the derivative of y with respect to t, and that's a normal derivative, so I'll put y dot of t. So let me stop, see if you're following. Okay. Yes?
What are the dots are the derivative of?
Yeah, these are the derivative with respect to t.
Okay.
So if you want, if I wanted, I could make that dx dt there, and if that's a little clearer, Danielle.
Okay.
Like that, does that make sense?
Yeah.
Okay, what is the derivative of x with respect to t? What is?
U1.
Almost.
It's just t.
Not that either. So let's write up the formula here. Constant plus constant t. What is dx dt? What's the derivative of this right-hand side with respect to t? What's the derivative of that? 0. What's the derivative of this? U1. It's just the constant. It's just the number in front of the t, right? The derivative of this expression with respect to t is 0 plus, if this was 1 plus 3t, the derivative would be 3. But here we just have a u1. We don't know what u1 is. It's something we can pick a little later on. What is, so let's write here dx dt equals u1. And then tell me this, and similarly, let's do a mathy thing here. Similarly, what is dy dt? Just take, don't say it out loud, but take a minute and see if you're pulling this together. Try to answer in your head, what is the derivative of y with respect to t using that parameterization up there. And I hope you're thinking you too. I heard it kind of like whispering on the wind there, for sure. Does this make sense? And if not, let me know, and I'll fix it. I'll try to fix it. So this formula becomes beautiful now. So this formula, this derivative of f in the direction of u is actually partial of f with respect to x at the point of interest times u1. That's just normal multiplication, plus partial of f with respect to y at x naught, y naught, times u2. And that's it. But we're gonna make this prettier because that sure looks like a dot product, doesn't it? Something times that plus something times that. And in fact, that is exactly this dot product. So I'm gonna write a vector here. It's partial of f with respect to x at the point, partial of f with respect to y at the point, dotted with u1, u2, my direction vector. And that is a dot, bless you, that is a dot product now. This has a beautiful name. Anybody know what that's called? Yeah, I'm hearing a lot of weird stuff. I don't quite know what it's being said. It's called the gradient of f. I'm hearing just muttering. It's almost like stream babbling in the distance. It's called the gradient. So this symbol here, this del, is a symbol. And the way I read this is the gradient. Have you heard that before? Physics people must, chemistry people must. Yeah. The gradient of f at x naught, y naught. That's how I read that. And the gradient is a vector. So it's a vector function, in fact. And then this is just the direction vector. So we can write this formula in a super beautiful way. This is gradient of f dotted with the direction vector. And that's your directional derivative formula. Where's my filthy rag?
On the table here.
Thanks. Oh, it's right by my stuff. Oh, good. And it kind of works for most of this to erase. All right, let's do some practice. So the first thing I think you also want to write by this is that this, so just summarize really quickly on your notes that this, make sure that's a U, equals this. This is how you compute it. And this is called the directional derivative. In the direction U, in direction U, and we make a note here, U is a unit vector. It has to be, otherwise it will contribute value to this that makes things incorrect when you're looking at the magnitude of the slope. So we don't want this to contribute anything to the slope value. And really what this is equal to is the slope of the tangent in direction U. Does that make sense? Cool. So let's do some stuff. So if I say I've got z equals x squared y minus, oh god, I hate this word, xy squared, start out chill. Get a new pen. Maybe this pen will be magic. Let me rewrite that so that it's legible. Oh yeah. There we go. That's some weird surface. Don't know what that surface looks like. I personally don't know what that surface looks like. It's kind of yeah, some weird thing. I can kind of picture it, but I don't know how to describe it. So let's find the directional derivative at, let's see, let's pick a nice point, let's say 1, 2, and then that would make the z coordinate 2 minus 4, -2. I think that works. Find the directional derivative at u in direction u equals, and let's just be nice here, 1 over square root of 2, negative 1 over square root of 2. And we're going to spend a lot of time today talking about the gradient, talking about these derivatives and visual interpretation, so that when you get out of here today, I think you'll have a good understanding of what's going on. So, step 1 is I'm going to find the gradient. And this is the f of xy that I'm interested in. So take a minute and find that. Gradient of f is equal to, and this will be a function. Don't plug in any points yet. Get the function first, the vector function. So remember, this is this, and let's put the reminder of. Start working this through. Should get something like that. You can sanity check for me too, seeing you all nod affirmatively, that's helpful. And let me know if there's any questions on that gradient. Step 2 is evaluate the gradient at the xy. We don't need the z. We don't need the z coordinate here. It's only the x and y. So at the x coordinate and the y coordinate. Z is irrelevant for this gradient, not always. So yeah, and then you plug that into here. Oh, that turns out kind of cool. Tell me if I did okay. Anybody else get 0, negative? Okay, yeah. 0, negative 3. Might have to get somebody to get out Desmos for me, because I kind of want to maybe look at one of the level curves of this thing, but let's hold off on that. So is there any questions on getting any of this stuff? Oh, good. I'm going to take that as everything's cool. Step 3 is find the dot product between the gradient at 1, 2, and my unit vector, which is already in a unit form. And so then that's going to be 0, negative 3, dotted with 1 root 2, negative 1 root 2, equals positive 3 over root 2, whatever that is. It's a little more than 2. Because this is 1.4, and that's almost half of 3. But it doesn't really matter, because one thing I gained from this is some knowledge that I wouldn't have had otherwise. So if we were to look at the level curves of this thing, and I might want to get that. So like I said, maybe we'll pull out Desmos here in a minute. Cause yeah, I don't think I can sketch that freehand quickly anyway. But what we know is that when we're at the point in the XY plane looking at level surfaces, so Z-axis coming out this way, if I look at the level surface that goes through -2, and I'm at 1, 2, so right here, that point, this is on the level surface, Z equals -2. I know that because that's the Z coordinate. And if I were to find all the XY points where Z was -2, I would get some shape here. But right now, I've just got this point. And I know that if when I look in that direction, so let's see, 1 over root 2, it's like this, -1 over root 2 is like this. So I'm looking down and to the right. I'm looking in that perfect diagonal direction, down and right. When I am on the surface, facing in this direction, I'm moving up at that slope. So I know that the slope here, the slope in this direction, at that point, is 3 over root 2. So I know that Z is moving up in value. So Z increases in value when I move this way. How are we feeling about that? Any questions at all? We're going to do more examples. We'll do lots more stuff with this. Okay, cool. Yeah, sorry.
Do you have any announcements?
No, you gotta go?
Yeah.
Yeah, go.
Do you have any announcements or?
No, I mean, just make sure to watch the recording. I don't have any announcements that I know about.
Just the quiz on Friday?
The pre-quiz. Yes, sir. Yeah. Yeah, let me know if you need anything, okay? Okay, so let's look at some cool facts here. Let's see if we can figure out a few things. Let's talk about the magnitude of this thing. So now, this is a scalar, right? This directional derivative is a scalar. It's the slope in the direction I'm looking. So just think of that, this is a scalar value. So these are absolute values. So I'm thinking about the magnitude of this thing. This is the magnitude of the gradient at that point. Now that is a vector dotted with u. Actually, sorry, take these off for a second. I apologize. Take these off for a second. Let's just talk about that. So that's just the definition of it. But remember this relationship. U dot V is equal to the magnitude of U, magnitude of V, times the cosine of the angle between the two things. Remember, we use this to find the angle between two vectors, where U, V, theta is that angle between the two. So this thing up here is equal to the magnitude of the gradient times the magnitude of U times the cosine of the angle between the gradient and the direction I'm looking. So let's actually draw a picture of that. So theta here is the angle between the gradient at that point and the direction we're looking. That gradient is something that just is inherent to this function. We can't control this, but we can control u. We can look in different directions. So maybe draw a little picture here that shows gradient and u and theta between them. Now we can kind of gain something really cool from this. When is that 0? Yeah, perpendicular. Yeah, when the vectors are perpendicular, the dot product is 0. So when theta is 90, pi over 2 rads, 90 degrees. So think about what that means. Let's say here's a level curve. Here's my gradient. When the u is perpendicular to the gradient, the rate of change is 0. That's like walking along the line of constant height. So if you're not changing height, and for a moment you're not, so if you are walking tangent to the surface, at least perpendicular to the gradient. I guess I haven't justified that the gradient is this normal vector yet here. But when this happens, there's a 0 rate of change. So right here, the directional derivative of f is equal to 0 when those two are at 90 degrees. And that would also work on this side as well. So either of those u's. So when you move orthogonal to the gradient, you don't move up or down at all. You stay constant. When would that be maxed out? When is cosine at 1? What angle? 0, yes. So let's put this up here. So we know that cosine of theta equals 1 when theta equals 0. What does that say about the gradient and the direction I'm looking when theta is 0?
Yep, you're looking like perfectly downhill.
Or I'm looking perfectly down the gradient.
Yeah.
Yes. So when this happens, we are looking in the direction of, because it could be uphill too, right? Yeah. Direction of the gradient. So when I'm looking at the direction of the gradient, this angle will be 0, and this thing will be at its maximum value. So let's think about what that means, i.e. when u equals the gradient direction turned into a unit vector. So when we're looking in this direction, this is the direction of the gradient, I have to normalize it so that it's a unit vector. So this is unit vector in the direction of the gradient. What does this look like then? Let's take a look at what this product looks like. So that is going to turn into, let's just do the scratch over here and put the summary right over there. D in that u of f of x naught y naught is the gradient, as always, dotted with u. But I'm saying let's let u be that. Dotted with gradient divided by the length of the gradient. We're almost done. There's some stuff coming. We're about to see something cool. This is a vector, this is a vector, this is a scalar. So let me rewrite this one last time. On top I've got the gradient dotted with itself over the length of the gradient. What was this? Remember, recall, there's lots of recalls today. If I take V dotted with itself, what do I get?
Magnitude?
What was it?
Was it magnitude?
The magnitude squared, yes, is the magnitude of V squared. Think about that. Let's just, like, if you're like, what? If V is V1, V2, and I dot V1, V2 with V1, V2, I get V1 squared plus V2 squared, and that's just the length of the vector squared. The square root of that is the length of the vector. So this is the length of V squared. So this on top is the gradient squared, the length of the gradient squared. And then we see something really pretty happen. So that's just that on top, divided by the length of the gradient. And look what we're left with. We're going to cancel one of those out, and we just get the magnitude of the gradient. So what does that mean? What that means is that the most this thing can be is the magnitude of the gradient. And it's when I'm looking in the direction of the gradient. That's what this computation over here implies. So it's equal to gradient, the magnitude of the gradient, when theta equals 0. So this here, let's make a few notes. This is when u is perpendicular to the gradient, and this is when u is in the direction of the gradient. And we could prove in a similar way, and I'm just going to kind of put this up here, that the least that could be is when theta is pi degrees. Pi radians, which puts you directly opposite the gradient. So and we could work this whole thing through again, that the least this derivative could be is the negative magnitude of the gradient when, and let's just put the, put when theta equals pi radians, i.e. u is opposite the gradient direction. Okay, so now let's do some stuff. That's kind of, there's a lot happening today. Let me stop for a second, let you get caught up. Let me look at my notes and see if I'm missing anything I wanted to say. Yeah, I think we should look at some gradients, like just some examples. For sure we should. Okay. So actually, let me just write some English that goes with what I just wrote there so that you can interpret that, because it's more important to understand the interpretation. So, what does this mean? This means that we do not gain vertical change when we move orthogonal to the gradient. You do not change. You're moving along a level curve. This would be moving along a level curve. The most we could gain, the greatest rate of change, the greatest increase in the function is the steepest the derivative can be is the magnitude of the gradient, and that happens in the direction of the gradient. So the greatest increase is the magnitude of the gradient, and that happens in the direction of the gradient. So the gradient is always pointing toward the direction of greatest increase. And I think this is what you were thinking a bit ago when we were talking about it. Might feel like a long time ago, but I think that's where your brain was going with that. And that is in the direction of the gradient. So the quick summary here is grad F points in the direction of greatest increase. You move in that direction, you're going up the steepest hill. In the opposite direction, the steepest decrease is in opposite the gradient. So the greatest decrease is in direction opposite the gradient. So let's get that finished up, writing that up there, and let's look at a few level curves that we can actually sketch. Let's do a nice pretty one that feels good. Chill. Very chill. I like this because the level curves are what shape? Circles. We got pretty circle. When you check it out, it's all gonna make a lot of good sense in our minds and on the board, and we can draw it easily. So, looking at the level curves, we can make a little chart here. So when Z is this, the curve is this. So when Z is 1, the curve is unit circle. When Z is, see, I want this to be a perfect square over here because the radius is the square root of Z. So instead of saying 2 or 3, I'm gonna put 4 here, because then my equation looks like this, and that's a circle of radius 2. So this is Z equals 1, concentric circle. This is not great, Z equals 2. And then if I put 9 here, oh sorry, this is Z equals 4, excuse me. And then if Z is 9, got a circle of radius 3. Not great. Yeah, better. A little better. So we got concentric circles. Let's find some gradients. So first thing is I just crank out the generic gradient. What's that going to look like? 2x, 2y. Is everybody cool with that? Derivative with respect to x, derivative with respect to y. Cool, so let's find the gradient at some points. Let's find the gradient at this point. What is that point?
2, 0.
2, 0. So let's make a little chart here. Here's our point. Gradient at that point. So at 2, 0, which is right there, the gradient is what?
4, 0.
4, 0. It's twice the x coordinate, twice the y coordinate. And that says the gradient is pointing just like that. Does that make sense? That's the direction of greatest increase. Notice how the gradient is pointing perfectly, it's like a radial extension, right? If I take the radius of a circle and move it out this way and kept on going, that's where the gradient's pointing. Does that make sense when I say that? It's like a spoke on the wheel. So here you get the sense that the gradient is kind of the normal direction from the curve. Let's prove to ourselves that the directional derivative would be 0 if I move tangential to the circle. What direction? Somebody give me the direction. That one right there. What's that U? Somebody give me a unit vector that points straight down.
0, -1.
0, -1. Right? No, don't want any horizontal movement. I want to go down, and I want the total length to be 1. So if I take that U, and let's take that gradient there. So let's do the directional derivative. So directional derivative in the direction 0, -1 of f at 2, 0 is equal to the gradient dotted with our vector, direction vector, and you can see that that's just 0. So we literally have 0 change, moving tangential to the circle, which makes sense. We're staying on the circle if I move tangential. At every single point, if I'm always moving tangentially for just an instant, I stay on the circle. But I don't go up. I'm out hiking, just walking along the topo lines, right? If you're ever out like just bushwhacking, and you're trying to find the chill spot, you walk along the topo lines so you don't have to kill yourself. And the older you get, the more topo lines you look for. What is the directional derivative in that direction?
Also, oh,
Yeah, that's okay. Wait, so straight up?
yeah, you get 0,
0 as well. Yeah. What is the direction of greatest increase here?
1, 0.
1, 0. How'd you get that?
Because it would be like in the direction of the gradient.
It's in the direction, and we just want to make it a unit vector. So if we take the direction, and remember, it's always going to be in this direction. So what I think Christian, I thought you were doing maybe, was taking the gradient and normalizing it to 1, 0. Maybe that is what you were doing. Yeah. So in the direction 1, 0, at that point, see how easy these computations become once we've got this formula here. The rate of change is 4. So at this instant, if I were on this surface, and this surface looks like this. It's a paraboloid. And there's the z-axis. And then right here is the x and y plane. The tip's right on the xy plane right there. And the surface, the level surface we're looking at is at a height of 4. So it's just this circle right here. And the gradient that we're looking at is pointing. So notice how the gradient kind of, you think of it as living in the plane down here. So we're coming to this point, where was that point? 4, 0, or 2, 0, excuse me. So 2, 0, this point right here. That gradient is pointing out this way. I should be using multiple colors here. But that's telling me that when I'm at the corresponding point on the surface, that moving the XY coordinates in this direction gives me the steepest increase that I can have. Let's do some application. I got more applications. They're like chemistry things or something. Don't ask me, you're the experts. Oh, there's a hot plate. There's a lot of hot plates in Calc 3. I don't know if you find them in your physics classes. In thermodynamics, do you study hot plates?
Yeah, we take thermos.
You don't have to?
I have yet to.
Oh, you have yet to.
For the
Who's taking
physics
thermo?
one, not really.
Oh, okay. Yeah.
Just magnetic plates.
Yeah, they would be good in that shit too, looking for the greatest flux or something. I don't know. Just making up words. So we're gonna do two applications.
Yeah.
So T at XY, that's a temperature given by 130 over x squared plus y squared plus 1. That plus 1, make sure you don't divide by 0 at 0. So that's a common kind of thing to see when you see a quotient like that. So this equals the temperature in the plane. And I'm assuming we just have this homogeneous plane that just goes on forever and ever. Temperature in the plane at XY. What happens as you move? Where's the max temperature at?
0.
At 0, 0. Yeah, when this piece is dead, you've got 130. So let's actually make a little bit here. So right here at the center in the XY plane, the temperature is 130. I don't know, degrees, sure, degrees Fahrenheit. Why not? That actually sounds pretty reasonable. No. Celsius sounds better. Yeah, I like Celsius. Yeah. It is a little more scientific, yeah. We want this to be rocket science for sure. So 130, that's the hottest. As I move away from the center, the temperature decreases in every direction. What do the level curves look like, do you think? So let's take a look at the level curves. So they're gonna be 130 over x squared plus y squared plus 1. What do you think those are gonna look like? Where will the temperature be constant? So what would make this value here a constant? Well, this is a constant. This is a constant. So what would happen if this was a constant? What shapes are those? Circles. So we have, when x squared plus y squared is constant, we have a constant value here, and that means the temperature is constant. So our level curves are going to be circles, just kind of like we just saw. The difference here is that as we move out, the value, the height is actually decreasing. If you were to look at this surface, if you were to sketch this thing out, it would kind of look like a 3D, like imagine there's like a little thing under a sheet. That's like 130 right there. And this thing's extending in all directions infinitely, but it's dying off. So think like a bell curve that's been rotated. Does that make sense? You think of like a standard bell curve just rotated? That's essentially what this thing kind of looks like. So as you move away, the temperature decreases on these level surfaces. And eventually it approaches 0. So for very large x and y values, the temperature is almost 0. Does this sound okay? Yeah, just want to gain some intuition about this before I start asking you some shit. Okay, so the first question, what was shape of the level curves? We know that. Where's the hottest point? We also know that. This is one for you. Find the direction of greatest increase in temperature at the point 33. And now you get to piece some stuff together. And I get to pee, and everybody's happy. Well, I'm happy. And then I would ask you, what is that rate of change? So find the direction of greatest change, of greatest increase at that point, and what is that rate of change? Grab that. Oops, sorry. might even be able to like gain a sense of what that direction should be. And then check your answer based upon that. If you just think you're standing on one of these circles, where's the steepest increase? What direction? But do it with math. That's the cool part. You already got this all rocked out, Kayla. No. Okay, okay, cool. Okay. No, that pencil's standing up hella good, that's for sure.
Wait, right now, you write that.
Well, I'm gonna make you walk me through it, Alex.
That's the greatest thing.
Okay. No, you're gonna at least give me the steps. What is, yes? Oh, you may check, yeah.
Did I just write this properly?
No. Maybe we should talk about that more. It's close. Alexander, just tell me one thing. What word? And you even mentioned it. You said I was talking about this earlier.
Okay,
I need the gradient, right?
I got that part.
Good shit.
Well, I mean, I know
That's
this.
partial credit, man.
So,
That's partial credit.
I'll take it.
You'd have to do the quotient rule. I'm pretty sure it's just 0.
I would rewrite that function like this because what? Don't use the quotient rule. I mean, you can. Did anybody use the quotient rule? No. They're like, I didn't even think of the quotient rule. Well, that's good. Because it's just kind of a waste of time because there's no variables in the top. And I know that's why you didn't use it, because you saw that. So then we do our partials, and we can spare the of x, y here. So I've got 130, bring down, so you had this part right, didn't you? Definitely do that. Leave the inside alone. That was the part that went afoul for you. Times the derivative of the inside with respect to x.
Oh, okay.
You kind of put them together,
Yeah.
which is a classic maneuver. It is a classic maneuver. No. I've seen that a lot. How does this look? Do I understand that chain rule? Derivative of the outside times the derivative of the inside. Why don't you do this one for me? If you didn't do it already. If you know how to do school, you just copy this down and put a Y there. That's school.
That's not math.
That's not math, that's school. Looking for exploits. And I almost feel like in this world, knowing how to exploit things is probably, you'll be a wealthier person. You won't end up a mathematician or something like that. Maybe you'll end up taking out some of the richest people in some way or another. Sorry, I guess I'm not gonna go down that road. But the gradient, I would write this out just because it's pretty to see, and I would simplify it because that -2 makes a beautiful fraction. So we've got x squared plus y squared plus 1 squared. And then on top I've got -260x. Does that sound right? Okay, cool. And then this one is going to be similarly -260y over x squared plus y squared there.
Oh, yeah.
All good? Yeah. And now I would plug in the 3,3. So what we are interested in is the gradient at 3,3, and that will tell us the direction of greatest increase. it's not pretty. Gosh, I don't even know, what is this, 26 times 3 is 78? You know, negative 780 over 9 plus 9, 18, 19 squared. This almost looks divisible by 19. And then negative 780, this same y coordinate, so we don't have to. Is that so? I don't know if that's divisible by, wow, that looks like a degree.
It turns out to be like a decimal.
What'd you get?
I rounded and I got a 2.16 for final.
That's good enough. Thank you. So that is not a direction, but it is at least a vector. We would have to normalize that to get a true direction. We would want a unit vector for a direction. But that basically says that you need to head, we're at 3, 3, let's say this is 3, 3 here. We need to head directly toward the center, which we could see that here. Of course I want to walk straight toward the peak, right? That thing's all symmetric. So of course I want to walk straight toward the top. And that's what the gradient's telling us here. So what is that rate of change in that direction? How do I find that? Yes, so you are correct, sir. So, but what is, so the directional derivative, and let's say that u is this vector that Daniel cranked out for us, negative 2.16, negative 2.16, normalized, which isn't going to be pretty. So I'm divided by its length, let's say that's that. Then what is the directional derivative at 3, 3? What is that direction? When I'm moving in the direction of the gradient, what is the magnitude of that derivative? And this is like, do you recall us talking about that? It was over here.
It was the magnitude of the gradient.
It is exactly, it's the magnitude of the gradient. That is the steepest things can be. They are the magnitude of the gradient. So this slope right here, the directional derivative is the magnitude of this gradient. See, I still have to freaking find it. And make a little note here, that this is the magnitude of the gradient of f at 3, 3. And gosh, let's just do it. That's not too bad.
I've got an answer if you wanted to.
Yeah, thanks. What is it?
I rounded it's 3.06.
Nice.
You guys get it?
Cool. Thank you.
No. Did you, for the length or for the normalized vector? Because for the length I got 3.06 and the vector is negative 0.17.
Oh, when you normalize, it was,
Yeah.
what was it?
Negative
Oh, I didn't know.
0.17.
I just.
Okay, cool.
Or 7.1, my bad.
7, okay,
Yeah.
okay, yeah, that sounds right. Thank you. Cool, lots of fun. Love hanging out with nerds. It's good shit. People care about such things, and I do too, so that's awesome. Makes my life so much happier. So let's say that x and y are in centimeters. What are the units on that 3.06?
Temperature degrees per second, yeah.
Yes, there's no time yet, but it is
Degrees per time.
per distance. So degrees, because the only thing we have, because the x and y's are changing with their centimeter changes, right? So our inputs are centimeter changes. So it's degrees Celsius per centimeter. Just at that moment. Yes, sir.
For this problem, do we need a normalization vector?
Not really.
Okay,
No.
I was wondering what you were doing.
I don't want to say that, Brandon.
My bad.
I didn't do it, I just didn't know if I needed to do it or not.
No, you don't need to do it, but it's cool that he did it. That's what I think is awesome. Because if you know, you might have to go through this and then you end up deriving that fact there anyway, but yeah. That seems like enough for one day. That's a lot. That's a lot. We'll have some more fun on Friday, I promise. Thank you. Thank you. Oh, yes. So, skill check corrections, please get them to me by Monday, from the ones you just got back, and we can figure out coming in and stuff as we need to. Thank you. Good. Would you mind, Christian, use that stop for me? Thank you, sir. Of course.